Uh, okay, so we are on. So welcome to this very interesting webinar, especially those of you who have been taking our course in group theory and representation theory, even though at the at the basic level, and also some of the mathematician on audience who whose research is partly intercepts representation theory, like our friend here on the audience, Palav. I will hand over to him to introduce before we hand to Johannes. So this should be hopefully a very inspiring talk, not just for you guys in the quantum formalism community, not just the mathematicians, but also the people doing grad research. So it's a pleasure and a great honor to have our friend Johannes Jakob Meyer, who is a PhD student with Jans Eisert at the Dahlem Center for Complex Quantum System at the Free University of Berlin. Johannes's research interest revolves around quantum information theory, especially quantum computing on NISQ devices, quantum machine learning, and quantum metrology. Johannes also enjoys working on fundamental aspects like learning theory, as well as working on applied issues at the boundaries between classical and quantum. So it's really great to have Johannes to give this talk, not least on the context of the current challenges that we are currently running. I don't know, maybe some of you are not aware of it. We are running a hackathon challenge. One of them is to do with the classical to quantum data encoding. The other one to do with trying to implement federated learning on a NISQ setup. So yeah, quantum federated learning on a NISQ setup. So yeah, without any further ado, I will hand over to Johannes, and then at the end of the Q&A, we will have our friend also Palav to introduce himself.
Okay, yeah,
So
thanks
Johannes,
for the
yours.
very kind introduction. Yes, I hope you hear me well. If you don't, then please say something. And if there are any issues with the slides, please also say something. Otherwise, I'm very happy to be here. I'm very happy to have such a nice audience, and I'm extremely happy to tell you about this rather recent work of ours. So I'm going to talk mostly about contents of a recent preprint that we put out that was also now accepted into PRX Quantum and will hopefully be published soon. And it's about how we can use quantum machine learning for classical data and how we can, in this context, exploit symmetries on the level of the data. So first, quantum machine learning, as you might have thought, it involves quantum computers to do machine learning. And obviously, there are many different ways of doing this. So, for example, if you just like imagine, you have a very powerful imaginary quantum computer, what you can do is just like, I don't know, train GPT-4 in superposition and do these kinds of things. Yeah. But we're not there yet. So we only have very small quantum computers. They're very noisy. They're not very good. And so we try to understand how we can also make use of these quantum computers. So how we really can squeeze something out of them. And as I said, like the focus of our paper was on quantum machine learning for classical data. So in this case, we really want to see that, or we really want to follow up on this very recent success of classical machine learning, or what very recent, yeah. So at least this like explosion of machine learning has been very recent. And also, for example, these transformer models, which are extremely powerful. I mean, all of this has been super successful. And people are like, oh, we have quantum computers and we have machine learning. What happens if we fuse those two together? It can only become more awesome, right? And yeah, this is like this field of QML. And this is where our research also revolves around. Now, so we have that in classical machine learning, we have used these, like, for example, these transformer models, neural networks. And then the question is like, can we also improve upon this, or can we just like at least do something useful when we use a quantum computer to express a learning model? Yeah. So, and to do that, we kind of need to take the classical data, and it somehow needs to go into the quantum computer. Yeah, because quantum computers, they always need to use quantum states to do the computations on. And there are some small problems, for example, like this no cloning principle. So if you get, like, for example, data already encoded in a quantum state, you cannot just like make another copy to do more complex processing, but you have to make do with this one copy that you have. So it's really like a subtle thing how the classical data enters the quantum computer. And now, obviously, how we do this in a very sensible way is extremely central for doing quantum machine learning with quantum learning models. And obviously, such an embedding has to be practical, scalable, and useful. So I want to say with that is that obviously you can encode a lot of data, but not necessarily so that you can do something very useful at the end. And practically also in the sense that you have to be able to realize it. And this is extremely pressing nowadays in this like context of NISP devices, near-term intermediate scale quantum devices that are just like small and noisy, where you really have to be very careful with how much resources you actually spend. Scalable, I mean, it's kind of in the same idea. It should also kind of at least be able to extrapolate to a setting where there might be an advantage. Obviously, if you only had 5 very noisy qubits, you will not be able to do anything useful with that. Speaking on like a really industry perspective, for example. But at least you want to have that the stuff you are doing has like an idea of like scaling up to where it could become actually useful. Okay, so without further ado, we have this problem kind of taking classical data and putting it into a quantum computer. And one approach, and this is the one we kind of look at in our paper, are so-called variational re-uploading models. So in our case, it looks like this. So I hope you see my laser pointer. Okay, my laser pointer. So you start from some kind of initial state on the quantum computer, and then you perform some parameterized unitaries. Usually you will say, okay, my quantum computer, it can implement some sort of gates, Pauli rotation, something like this, and we can parameterize them. And then what you do to get the data into this whole process is that you do like a parameterized unitary, but parameterized by the data. So for example, you can imagine that you have some pixel and you kind of have this value is from 0 to 255, and then you map it to 0 to pi and use it as an angle of a rotation. So now you have the data dependence, but really as a unitary. Yeah, it's not like you put the data into a state and then feed it into a model, but it's really you kind of have a unitary that encodes the data. And this is nice because you can just like reuse this unitary multiple times in a circuit, as we're doing here, and interleave it with these like parameterized blocks. And this is kind of useful to circumvent this problem that you have this no cloning principle. So either you prepare a lot of quantum states that encode the data and feed them into a model, or you do it, which is kind of the parallel approach. So you do it next to each other, or you do it like in depth sequentially. And this is what we are doing here. And this is obviously much more amenable to like these small quantum computers where you have like a bounded space, so to say. Okay, so this is the kind of model blueprint that we want to use in this work. And obviously, when you see this, you immediately ask yourself, okay, how would we even design these unitaries that embed the data? So this is really a very crucial point. And obviously also, how would we parameterize the trainable parts, so these Ws? Okay, and because it's not necessarily clear a priori what should be good. Yeah, I mean, also with neural networks, for example, where you also have a layered structure. I mean, people have been doing this for a very long time, and it took them a very long time to figure out what good ideas are and what not. It's a lot of trial and error. And so we have this need for these design principles, and we really need some informed constructions for those. And so this motivates the exploitation of symmetry. Okay, so what is the case for symmetry? Just like globally speaking, also in classical machine learning. So if you, for example, look at these two pictures, I hope you will agree with me that the left one is very cute and the right one is very cool. Yeah, and now if you look at these images and then think about like rotating them, 90 degrees, 180 degrees, minus 90 degrees, then you will probably agree with me that they are still cute and still cool. So you can say that these images they have a label invariance. That's what we call it. So it doesn't matter if you rotate the image, the label cute or cool is still the same. And mathematically speaking, we kind of have our data, which is this like axis, and here's the laser pointer again, these axes, and we have some kind of symmetry operation. Yeah, in this case would, for example, be a matrix or a linear operation that rotates the image, kind of permutes the pixels in a certain sense. And if I perform this operation, this VS on my data, then the label should stay the same. Yeah, for all of these operations in the symmetry group. And this VS is kind of what we call the original representation on the level of the data. And I mean, this whole concept of using symmetry to get like invariant predictions from a learning model has been extensively studied in the classical case, where this is called geometric deep learning. Okay, so now we have made the case that the symmetries, they're kind of nice because we can now say, okay, I know that my data has a certain property, namely this label invariance under these symmetries. And if I can build in this invariance in my model, I can construct a model in an informed way. It will have less parameters because I remove degrees of freedom. But I remove degrees of freedom so that the power of my model does not change, essentially, because I only removed superfluous degrees of freedom. So it's really like I rotate the image, and then essentially what I say is that my model will perform exactly the same way. Yeah. So I mean, I'm rubbing this point in, but it's really important. You just like really reduce the expressivity of your learning model in a way that does not make you lose any power. Yeah. So it's just like it's really good because the less expressive, the easier to train. Okay. So this is nice. And this has been really exploited a lot in the classical literature because there it's relatively immediate how the symmetries act on the data. But in our case, we have the problem that the data is not what we work on, but we work with the embedded data. So we really have to also track how the symmetries work together with these data embeddings. Okay, so what do we have? So I told you we embed the data, in our case, into unitaries. So we have this map U that takes the data into SU 2 to the n, which is kind of the unitary group on the quantum system of n qubits. Yeah, just imagine a very large matrix, a very large unitary matrix. And in our case, we also have the symmetry operation. So it's really like this map that on the level of the data maps data points to another data point which should have the same prediction. And then you can look at a small diagram which kind of captures this. And so you have on the left-hand side what's going on the level of the data. So you have the symmetry operation. And you always have this embedding of the data into the unitaries. And then the question that arises is, okay, how do the symmetries, so this VS, manifest on the level of the quantum system? So how do the unitaries change when the data points change? Because if we want to exploit the symmetry that we know exists on the level of the data, we also have to make sure that it is meaningfully represented inside or on the level of the quantum system. And how this might work, I want to show you in a toy example. Okay, so consider the following very easy learning task. So you want to do classification, binary classification. You have either the blue ones or the orange ones, and they are arranged as you see here. So this blue and orange shaded regions are kind of the ground truth. And as you see, this prediction here it has like two kinds of symmetries in the two coordinates. So first, you can kind of flip the coordinates, exchange the coordinates. This is like this green operation, which is just like really exchanging x1 and x2. And you have this other operation, which is the red one, which is an involution about the center. So you map x1 to minus x1, x2 to minus x2. And if you multiply those two together, you get a flip around the other axis, which is this purple operation here. So this is like our very small learning problem, two-dimensional learning problem that has like a Z2 symmetry. And we use this particular problem and we do a very simple unitary embedding. So we use a Pauli rotation that takes the first argument as the angle, and on the second qubit, a Pauli rotation that has the second data feature as an argument. And now we can look what happens if we perform these symmetry operations on the data. So 1, 0, so we exchange x1 and x2, and then what we see is that the arguments of the two rotations here are exchanged. And this we can as well realize by swapping the qubits before and after the operation, and then we get back the original operation wedged between those swaps. Similarly, if we do this involution about the center, if we add these sign flips, minus x1, minus x2, we can also realize this by putting like a Pauli X gate before and after. This is because xzx maps to minus z. This is why this works. And what we now say is that we want this to happen in general. So if I perform a symmetry operation on the level of my data, and I have fixed some sort of embedding, I want that I can recover the original embedding from after the symmetry operation, modulo some operations that I wedge the unitary in between. Yeah? And this is what we call an equivariant embedding. So an embedding that has this property, and in pictures it looks like this. So you start out from a unitary, you perform the symmetry operation on your data, and then we want this to look like this. So we have this US unitary happening before and after, S obviously the same as the VS, the group element that we use to act on the data. And left thing is what we before called the original representation, and the purple thing is now what we will call the induced representation, because it's a representation that is now acting on the level of the data in this at the level of the quantum system as it transforms the unitaries to this adjoint action. Yeah. So this is kind of what happens if you have a so-called equivariant embedding. Yeah. And so you see here that this embedding here is equivariant under these particular symmetry operations. But I want to underline that this is not generally the case. Yeah. So this X, or I mean, I have it on the next slide. So I mean, this is how we define these equivariant embeddings. So we say, okay, the equivariant embeddings, they are such that you get this adjoint action as a representation of the group operation on the level of the quantum system. So it's really like just like transforming the unitaries. And really this existence of this operation is not always guaranteed. Yeah. So if you want to have an induced representation for the particular symmetry that you have on the level of the data, then you really have to make sure to construct it in a special way, and it's not always possible. So what I can say, for example, is that, I mean, there is always a trivial embedding in the sense that if you map the data to an identity operation, so if you do nothing, then obviously any symmetry transformation will also be well represented by doing nothing. Yeah, so this is kind of a trivial embedding, trivially equivariant, but it's very uninteresting. And if you want to have a faithful embedding, so if all of the group elements go to different operations on the level of the quantum system, then, I mean, for example, for very obvious reasons, this can only exist if they have faithful, finite different dimensional unitary representations. Otherwise, you cannot express it as a subgroup of the special unitary group. Yeah. So there are obviously more conditions that you could come up with. I mean, we didn't check all of these in our papers, but yeah, I would say we don't know what the full set of necessary and sufficient conditions is for these like equivariant embeddings to exist, for example. Yeah? Okay, but I now told you what these equivariant embeddings are, what we understand under this concept. I gave you this small toy example, and now I want to do a little bit more, detailed or a little bit more less trivial examples. So, for example, assume you have 3 coordinates with a permutation symmetry. So, I mean, I could do what I just did in the toy example, take every coordinate, put it in a Pauli Z rotation on a qubit, and then obviously permutations of the data points will be realized as permutations of the qubits. So this is all perfectly fine, but for 3 coordinates, you can actually do it a little bit more compactly. Yeah. So what you can do is you take 2 qubits, and then for every data feature, you take one of those mutually commuting polys, x, x, y, y, and z, z. And you can actually swap or kind of realize any transposition of elements of these 3 data features with a so-called generalized Hadamard gate. Basically, if you imagine a Bloch sphere, what you want to do is you want to map x to y and y to x, but leave z invariant. Yeah, that is not possible because every time you map x to y and y to x, you will map z to minus z. This is why we have to introduce another z here, because then z minus will go to minus z, so it's going to z again, so everything is fine. Yeah. So this is a little bit more of a non-trivial example. I mean, it's also in the paper, and there I think it's also maybe less in a rush. Yeah. Okay, but I mean, this is, for example, something you can do. And while discrete symmetries are extremely important, yeah, because I mean, for example, image data, I mean, it's always pixels. Yeah, pixels, they live in discrete arrays. It's obviously also from a mathematical point of view very interesting to look at, okay, what happens for continuous embeddings or continuous symmetry groups, Lie groups, yeah? And what we there consider is to say our data embedding, we now consider it as an embedding of the data into the Lie algebra of the quantum system, yeah? So if you go back to our pictures, it kind of means that we want to embed data really into this SU2 to the n, this Lie algebra of our quantum system. And I mean, that's also what we already did in all the examples I showed you before, because a poly z rotation with x as an argument is e to the minus I xz, up to constants maybe. And so this is already mapping into the Lie algebra, because you take x and map it to x times z, an element of the Lie algebra. Okay, and if you're now here, you have these continuous equivariant embeddings, then you can say, okay, I say it's a Lie group, so I can write every element as an exponential of some generator. So an element of the Lie algebra of the group that generates these, or the Lie algebra generates the symmetry on the level of the data. And similarly, I can do the same on the level of these quantum systems, where I say, okay, this adjoint action US dagger, I call it WS. And as I said, it's an adjoint action, so that's why we have this AD here. So adjoint just like means you wedge it, yeah, between US and US dagger. That's the same thing. And you can also see this as an exponential of an adjoint action of elements of the Lie algebra here. So what this essentially means, what I want to tell you with this, is that there is a feasibility condition. So we have this particular form, you know, this adjoint action with a unitary as a representation of the symmetry. This is what we enforce with these equivariant embeddings. And we have it when this feasibility condition is met. So for all, so I also have it here. So for all the generators in the Lie algebra on the level of the data, if you look at this diagram, essentially, we want this diagram to commute. Yeah, so I can always express these adjoint operations on the Lie algebra here, somehow related to the Lie algebra here on this part of the system. And what this essentially means is that you kind of need to find a mapping, a non-trivial mapping of the Lie algebra that you have here on the data into kind of this, what we call it, adjoint representation of this especially unitary Lie algebra. Yeah. So I'm a physicist, right? So I mean, for me, this is all more or less intuitive, and probably it's also a little bit more detailed in the paper if you want to have a look later. But I think there could also be much more said and much more be done on like conditions when this actually works, yeah. Because, for example, I mean, we have been looking a little bit into this theory of, for example, Dynkin diagrams that tell you kind of which Lie groups or Lie algebras fit into the other Lie algebras. But I mean, I think this this topic is still not fully explored. So there's a lot that one could still look at also in the context of these embeddings, for example. Okay, now I told you kind of what we understand under this equivariant embedding. and how this can be realized, mathematically speaking, at least. I mean, I guess it's probably a little bit confusing. That's why we go to an example now. So we go back to our 3D vector, but now we say it has an orthogonal symmetry. Yeah, so the group operation that you want to build an equivariant embedding for is now the orthogonal group. So it's like rotations in space and involutions about the center. And we kind of use a very similar embedding in a certain sense. So what we do is we take every data point, here x1, x2, x3, and we kind of map it to a point on the blocksphere, essentially. So we just like take x1 times x, x2 times y, x3 times z, and we append another poly x on a second qubit. So it's like a 2-qubit embedding. And why we do that is because we want to use the fact that O3 factorizes into SO3, which is addressed by this part, and Z2, so which we use this part for. So and then if we do this embedding and we have like an orthogonal transformation on the level of the data, the induced representation will become the following. So if we have an involution of about the center, this B is a 0 or 1, depending if we have it or not, and a rotation around an axis, n, by an angle alpha, this will be mapped, or the associated induced representation will be first a z on the second qubit that is just like either there or not, depending if I want the sign to flip. So this is the involution about the center. And I have this rotation here. So it's kind of a poly rotation, but the operator we rotate on the generator is given by an inner product between this same vector here and the poly operators. So it's kind of the same mapping here. So it's really like n1 times x plus n2 times y plus n3 times z. So it's just like a very similar operation. So here we also see this factorization. We have and we really have that SO3 and SU2 are kind of equivalent. And this is also why this is working so smoothly. Yeah, it has something to do, and I hope I don't get the terminology wrong, but this fundamental representation of SO3 of the Lie algebra is equivalent to the adjoint representation of SU2. And this is exactly kind of this isomorphism or equivalence that we see here. Yeah. So this is why this continuous embedding works so beautifully. Obviously, I'm showing you this, it works nicely, but as soon as you want to generalize to more complex groups, higher order orthogonal symmetries, you run into a lot of trouble. We've not been trying to push so hard because it's nice that we live in the 3-dimensional space. So usually 3 coordinates are enough, but obviously one could be interested in doing other types of data analysis where higher symmetries might be interesting, but because you don't have these beautiful equivalences, you don't have them anymore, you can really run into problems. Okay. Now, yes. So I told you that we want to use symmetry because it gives you label invariance. And now I've been talking a lot about how we design the data embeddings, these UXs, such that we get a meaningful representation of the symmetry on the level of the quantum system. But I mean, the initial motivation is that we wanted to produce an invariant model. So now we have to talk about how we do this. Before that, I will take a sip of my water bottle. Okay, how do we do this? So for this, we also, next to these equivariant embeddings that we use to have like a meaningful symmetry representation, we also need what we call equivariant layers. And these are the layers that commute with this induced representation. So this is like, if I have these blue parts, if you remember, these are the trainable parts of the model, and I say they really have to commute with the induced representation. So for all group elements, I want this stuff to commute. And why do I want this? It's because if I start out and I use 2 embeddings and there's like a trainable part between them, and then I transform the data with the symmetry operation, I can pop in these representations because we assume an equivariant embedding. Now I assume that the trainable part and the induced representation commute, then these two guys, they will annihilate, and then we are left with this object here. So we had the induced representation on the outside, and on the inside we have 2 times now this original block that we started with. Yeah. So what we do here is essentially by enforcing that this W commutes with this induced representation, this allows us to chain these blocks, embedding, trainable block, embedding, trainable block together, and only get the induced representation appear at the end of this whole chained object. So this is why we need to enforce this condition, because this will be useful to get like invariant models. Okay, so we enforce this condition, and with that, we get an invariant model recipe. So first, we start from an invariant input state. Yeah, I just showed you that we have like these blocks, and at the beginning and the end, we have these induced representation appear. And then if we take an invariant input state, so one which does not change under the induced representation, the state on the left eats up this left part, the left representation that was popped in. Then, we start from there. Then we do these equivariant embeddings and equivariant layers multiple times. And then at the end, we measure an invariant observable. Yeah, this means that on the right-hand side, we are still left with one representation. And we now say, okay, the observable as well has to be invariant. So it has to commute with this symmetry operation. And then it means that the observable eats the other end of the symmetry, which means that at the end of the day, all the US that have been popped in just like disappear, which gives us the invariant prediction that we were after. So really take an invariant input state, perform these equivariant embeddings and equivariant layers, and at the end measure an invariant observable. This is what we need. Okay, so this is really the invariant model recipe that we did this all for. Okay, now you might ask yourself, okay, we've been talking about these equivariant layers, these trainable parts have to commute with the induced representation, but how do we actually get this? And to do this, we introduce what we call an equivariant gate set. Yeah. So the question is, how can we actually construct these equivariant layers? So the ones that commute with induced representation. And how we do that is we say that, okay, if I use some gates and use them in succession, obviously, if each of them commutes with the induced representations, this concatenation as well. Yeah. So if I only use gates from a box from a gate set, which we call the equivariant gate set, that already commutes with this representation, then we are fine. So what we do now is we take a regular gate set. So for example, Z for a poly Z rotation, maybe a C0 gate on 2 qubits, these kinds of things. And we perform a so-called group twirl. Yeah, the group twirl is essentially a project. So, I mean, this, for the mathematicians of you, I mean, there's a thing called the character projector formula, which means if you have a representation like US here, you kind of can use the group and any character to project onto the isotypical components of the representation. And this is just like the trivial isotypical component that we project onto here with the trivial character. And essentially, the operation I show you, averaging over the whole group of this adjoint operation, gives you a projector onto the commutant of these symmetries here. It's actually super simple to check mathematically. And what we then get is this equivariant gate set. So we started from some elementary gates, probably the ones that your device offers you. Yeah, usually if you go to IBM webpage, I mean, the kinds of gates they have, they write it for you. You take those, then you perform this group twirl operation, and then you get some new generators that you can now use that kind of respect now the symmetry that you can always use to construct these equivariant layers. And as an example, yeah, what, for example, happens if you have an arbitrary permutation symmetry on 3 qubits and you start this group twirling process with a Z rotation on the first qubit, what you will get is 3 copies of the Z rotation with the same parameter. This is what essentially happens because to commute with like permutations of the qubits, you have to act the same on all qubits. Yeah, so this is really what falls out also of this group twirl operation. And in the paper, we have in-depth examples of this. Yeah, and the example that we use in the paper and that I also want to show to you now is a game of tic-tac-toe. So we did some numerics, and it's a classification problem. So we are given games of tic-tac-toe. So here, you know it, noughts and crosses. And we are asked to classify who won in this game. Yeah. So in this game, the circles have won. Yeah. And who won does not really change if I flip the board or rotate the board. So it has like a non-trivial D4 symmetry group. And why did we choose this example? A, because it's very nice to see what's going on symmetry-wise, and B, because we can implement it with 9 qubits. And this is more or less at the edge of what our small, poor laptops can simulate. So this is also one of the problems in this whole QML community that, I mean, we have a lot of ideas what we could do, but we cannot really test them because we don't have large quantum computers that we can work with. And we are also not able to simulate stuff as well as we would like to. Okay, but that's why we have a small scale example, and it at least shows what is going on. So what we do is we take this game plan that we're given, convert it to numerical values, and then we kind of take these numerical values, convert them again to angles. Yeah, so we just like equidistribute +1, 0, and -1 on a circle. And then we perform a Pauli X rotation corresponding to these angles here on every of the qubits, and the qubits map 1 to 1 to like the game plan that we are given. And the equivariant gate set that we now use, that we also obtain from twirling under the symmetry operation, means that if I have a single qubit gate acting on one of the corners, I have to perform the exact same single qubit at the same time and on all of the corners. Same with the sides, same with the center. Yeah, and you get this also from just like taking this unit cell here and just like flipping it around using the symmetry. And for the entangling gates, because you also need to construct some entanglement, you have that, for example, if you have an entangling gate acting between a corner and its nearest side, you have to do it for all pairs of corners and nearest sides to make it equivariant. And these are the 3 types of gates we use here. So it's like really corner with side, side with middle, middle with corner. Yeah, and with these, we again construct some circuits. And I hope this is more or less clear. And in our numerics, what we do is we try to identify if these models or if the symmetrization procedure gives you an advantage. Yeah, and so what we do is we take a regular reuploading model, and then that is just like constructed from a regular gate set. Then we say, okay, what would have happened if we had instead used the symmetrized equivariant gate set and compare those, and we do sweeps over different staffs and randomized architectures to see if we don't cherry pick any examples. And we see that on the training data, the performance of both is more or less equivalent, which is also expected because you don't need a lot of training data to get to the best performance in this particular problem. But what we also see is that the invariant models, they have a really better generalization capability because obviously they have this inbuilt constraint to respect the symmetry of the inputs, right? So, and we see that it's also a generic thing because we really tried it for randomized architectures. So we really try to not cherry pick anything. Yeah. And with that, I'm coming slowly to the end of this talk. So in our paper, we also have further results. So we perform analysis of different kinds of symmetries, both continuous and discrete. I showed you some already. We discuss obviously the problems that can surface when you use this, for example, this group twirling procedure to get an equivariant gate set. We have more numerical experiments that showcase an improved generalization. And we also show that you can use this, for example, also in quantum chemistry, in VQE, and if you want to find ground states of Hamiltonians. And we also show that this mitigates barren plateaus in certain regimes. And then with that, the summary. So if you want to do machine learning in general, you need a good model. And especially in the quantum setting, we really need informed choices of how to construct these models and these variational models, reuploading models I talked about earlier today. And I said that this label invariance that we use here, so which has also been a driver in this geometric deep learning in the classical setting, is a really nice informed way of doing this. Now, we show if and how such information, this label invariance and the group that is acting on the data, can be used to get an invariant learning model. And we also show that the models that result from our proposed blueprint, so to say, they have less parameters and they have a better generalization capability. And because I was told that you also seek some inspiration, I have some open questions. So first, obviously, these variational Lie uploading models, this is only one way how you could imagine the data to go into a quantum circuit, or to the data to go into the quantum computer at all. And I mean, is this the most reasonable choice? Are there other ideas that we could have? Especially as a side note, these things where you embed into the Lie algebra of the system, where you redo parameterized polyrotation, where the angles are, for example, depending on the data. This is a very near-term thing, in the sense that these operations, these polyrotations, they are not immediately available on a fault-tolerant quantum computer, because a fault-tolerant quantum computer always has discrete building blocks. So you have to use a lot of discrete building blocks to make a very small angle rotation, for example. So depending on the capabilities that we assume, these models might be more or less reasonable. And obviously, second question, I mean, what else can we do? And how reasonable would it be to do this? And the third thing, which I want to say is, right now we don't even know if using quantum machine learning, especially in the form that I showed you today, if this is a good idea in the first place. I mean, you could say that, oh yeah, if we get quantum computers one day, it might be a good thing to do or not. But I mean, we don't know, because in classical machine learning, people also usually have not known if it was a good idea or not. And as such, everybody had to wait until everybody had to wait until people were actually running these large models and having very good results. And that has not yet happened in quantum, and it also cannot happen. We cannot simulate large systems, and the experimental platforms, so these quantum computers that we have nowadays, they're not good enough. And especially on this question, is that is for QML a good idea for classical data? It's also, I mean, why would this special structure that quantum computers kind of exploit, everything is kind of unitary, everything is rotating in a very high dimensional space, why would this be good for a classical machine learning task? So what would also a classical machine learning task have to look like to be very amenable to quantum machine learning? So all these are very intriguing questions, and I would also like to thank you for your attention with that. I'm looking forward to your questions. I also have a PDF of these slides that I already uploaded onto my homepage. You have the QR code on the left, and I put a QR code with the archive link of the paper. And with that, I hope I didn't leave you any more confused that you came into this talk, and hopefully a little bit, more excited about this whole topic. And I think the bottom line of everything I want to say is just it's intriguing. So there is a lot of open questions. We don't know if this is a good idea in the first place. Like in classical machine learning, the people were just trying it out and it worked. And here we can't try it out. So I mean, this is especially means that theorists, mathematicians, and so on, I mean, really need to push to have really analytical results that tell us, oh, this is a really good idea. This is a really good thing to do, because that's the only thing we can do nowadays. Yeah. So with that, thanks a lot. I hope you had fun, and I'm looking forward to your questions.
Yeah, thank you so much. It's it was very interesting. I'm sure everyone on the audience and yourself, Pallav, I hope it was also inspiring, at least in some of the mathematical questions that he was alluding to at the beginning. For example, to prove, to have some sort of a general proofs for some stuff that was going through. Let's see. Do we have any questions? I see a lot of the chat open. What I could do is actually I will open the stage for some people, because sometimes it's very hard to see the test. Or people make typos and it's hard. So I will open the stage, and then if somebody wants to ask a question, you can just join the stage. Yeah. So Pallav, you as a representation theorist or someone working in representation theory, is there anything that caught your attention or something? Anything interesting?
Yeah, actually, I did have a question which is related to a question I think which was asked in the chat at some point. So you talked about having a certain groups, a certain symmetry group acting on a data set, and then transforming that to get some representation of that in the unitary group.
Yes.
What if that? What if instead of? I mean, I guess I know some answer for this, but I would like your take on this. That instead of doing this transformation, we first consider the set of orbits of the group action on our data set, and then try to embed that into whatever kind of data encoding form. Basically, we remove the aspect of the symmetry beforehand rather than embedding that into the symmetry in the unitary group.
Yeah, I mean, obviously you can do that. But I mean, what you're then doing is you reduce to just like regular machine learning without symmetry, right? I mean, it's just like more or less the most general reduction you can make. And in a certain way, people, okay, let's say like this. I mean, this is obviously like true. What you're saying is you can do this. The question is like if you should. Yeah. And especially in these quantum things, or I mean, obviously, everything I now say, you can also do in your framework, kind of. So, for example, sometimes you will only want to kind of implement a subgroup of your symmetry because, I mean, maybe kind of your model is trivialized too much or the expressivity hampers too much if you do implement a too large symmetry invariance. For example, what also can happen, which is we also have like a section about this in the paper, is that if we have a very universal overparameterized, so to say, model, is overparameterized, it has a lot of parameters, it's pesky, it's not very good in that sense, but the loss landscape looks very good. Yeah, you can, if it's very overparameterized, you can usually just like walk to the global minimum, everything is fine, convex, super good. However, if you start enforcing like symmetries and too many symmetries, somehow it can happen that your loss landscape becomes super ugly. So you have way less parameters, but you have a much uglier loss landscape. So in these problems, there are really a lot of trade-offs in how you implement symmetry and not. Yeah, so, but I mean, obviously, if you only implement a subgroup of the symmetry to say, okay, I don't want to reduce the expressivity too much, you can also say, okay, I just like take the orbits under the subgroup, remove them, and then I do classical machine learning. Perfectly true. I mean, it's kind of, yeah, either you can do either, right? The question is just like, I mean, how would you in practice do it? Maybe it's just like also a hassle to kind of, yeah, remove the orbits and normalize for the orbits. Another thing is, and I mean, we actually didn't do this in our paper, but you also usually only have like approximate symmetries. Now, for example, what people usually say, one symmetry which is happening a lot, which people also use in classical machine learning, these convolution layers, is you have an image. Obviously, if you move everything by 1 pixel, yeah, I mean, a cat, 1 pixel moved cat, still a cat, right? Yeah. Obviously, if you move the cat too far, you have half a cat. Yeah. So, I mean, what people in math do is, oh, the cat reappears from the other side. Yeah. Still, you have 2 halves of a cat. Yeah. Because, I mean, yeah, your image is not a torus. Yeah. So, it's, you see where I'm going. So, obviously, you have this kind of symmetry, but not if you go too far. Yeah. So, I don't know how well that fits in your framework of taking these orbits. Yeah. But I mean, there's like a lot of fine print that you at least have to look at. And yeah, I think it's like a very long answer to which didn't really answer the question, but I hope it was
helpful. This is an interesting thing to further think about, Pallav, as a point of curiosity.
Yeah, I think, yeah, that is a very satisfactory answer. Thank you so much.
There's another mathematician who had another question. I think it was Max. Somewhere I lost it. Yeah, so his question was about.
Yeah, I think his question was exactly like kind of what I had in mind too. Like we had a similar question too.
That's right. That's right. Yeah.
Yeah, he mentioned that you could quotient your data by the equivalence relation. So yeah, that's like considering the orbit space. And,
yeah. Was there any other? Does anyone want to come on stage? Let's see if someone is requesting. And Johannes, I guess on your paper you must have some sort of like a list of some of the groups, symmetry groups that you exploited and run your stuff with. Are there is that the case?
I mean, what was the question?
You must have on your paper some of the symmetry groups that you exploited. Yeah, on the paper, I guess.
Yeah, so I mean, like the thing is, what we do is we do permutation symmetries because they are arguably the easiest to implement and also the most relevant in practice because you usually have discrete data. But I mean, what we also do is we have this O3 example, which also captures SO3, any subgroup of thereof. And I think somebody was saying, I think my co-author Elias was looking into this. I think there's also the possibility to do SO6 or something like this because it's very related.
Okay, more exotic group. Yeah,
but I mean, I think that's what we cover. And I mean, it's kind of an open question to do it for more exotic groups. The question is like always, where do you get those? Yeah, I think like the probably more interesting direction now would be like approximate symmetries and how that kind of factors into this image.
Interesting. I have a guy here. Let's see. Martin, what about you? You are a string theorist. You want to come on stage? Let's see if he is available.
Yeah, by the way, I saw that there's Berend who asked a question because he has to go, and he maybe I can answer that before he leaves. So he says, can symmetry testing somehow be automated for more complex data? I think there's like a body of literature about this. I think there's. I think I also saw like a quantum paper, quantum symmetry testing, something like this. But it's like nothing that we particularly looked into. But it's just like, I mean, the literature exists, but I think it's non-trivial in a certain sense. I mean, I think the kind of answer of how well this works depends on the kind of question you have and what kind of assumptions you put in.
Yeah. It's actually interesting that this question about whether doing QML with classical data is a good idea.
Yeah. Yeah, I mean, the thing is like, it's really like one of these fundamental questions of the field that nobody knows. Because I mean, there's this large like development of these like NISQ applications, you know, with these near-term small quantum computers, noisy quantum computers, and people have been asked, okay, what can we do with them? It's not the same as what should we do with them. Yeah, so that's how people came up with these models and hey, can we use this? Can we do this somehow? People are, and I myself am as well, looking into this. But I mean, we still don't have like conclusive, I mean, we don't have any evidence, I would say, for this is actually a really good idea. Yeah, I mean, people try to understand this better and it's like the scientific process and everything. But I mean, this is one of the major questions in the field. Like, is this a good idea in the first place? And I really feel that maybe on a very high level, one can already say something about this. For example, if you say, okay, your data embedding is a linear map into the Lie algebra of the quantum system, maybe this is useless. I don't know. But I mean, it depends on what useless means. Yeah. But I think some arguments like this could be made in some way or another.
It's definitely very interesting. From my curiosity is actually, especially in this thing of how useful are the current NISQ devices are, is whether trying to network them together. That's also a whole new problem how to do that. In order to do like learning in a distributed fashion could actually lead us to something interesting. Yeah.
I mean, the question is like if what useful means, right? It's like
exactly.
You want to compete with machine learning models? Yeah, no chance in the next years. Obviously not, because like machine learning is so developed. But I mean, I think like really having like good proofs of principle would already be helpful because if you say, okay, we see something and we kind of see how this extrapolates to something useful at the point where we have like larger and better quantum computers, for example, that's like nice.
Yeah. Okay, so we have Martin. Do you have any question or any point you wanted?
I mean,
I don't know how early you joined.
Can you hear me?
Yes, we can hear you.
Okay, yeah. No, I mean, I was mostly in almost every the complete talk. Yeah, I don't have too many questions, but I am a bit like curious about the. I mean, he said that. I mean, there is no clear applications because you cannot know at this stage if the these formalisms works for a concrete problem. But I am a bit curious about if you can say something more about that, because I think about what is the advantage of this quantum machine learning respect to other to a typical machine learning, not only in terms of more faster speed of computation or whatever. Like, for example, I think that the quantum machine learning is proposed for some algorithms that are quite famous of quantum computation, like Grover algorithm or something like that. So I don't know, maybe this quantum machine learning exploits the physical symmetry of some concrete problem, but I don't really know how you define the if you know if some physical system has a concrete symmetry, and you can use this approach for that. I mean, if you can tell something more about a possible application, it would be good. Or
Yeah. So I think I'll just like maybe how I got the question so far is like, should we do quantum machine learning? This is a good idea.
Yeah.
On the high level.
Yeah. What is the state of the art in terms of what problems could be interesting to apply these formalisms?
Yeah, so I think the state of the art is like machine learning in the 60s. Yeah, it's like, I mean, somebody has like a computer the size of a house, and they can run 4 neural network on it. Yeah, so if you compare it to contemporary machine learning, it's like completely useless. Yeah, extremely completely useless. So for practical purposes, I mean, don't do it. Yeah. The thing is, like, this is an emerging technology. This is like really at the exact boundary of like our current knowledge of research. And I mean, people are trying to really understand how we can use quantum computers to do learning stuff. But for now, I mean, this is like nothing that has any obvious use in production. I mean, there's this thing that if you have a fault-tolerant quantum computer, what you can always do is it's called QBLAS, Quantum Basic Linear Algebra Subroutines. So, I mean, this is just like generic speedups for linear algebra operations. Some stuff that is just like going faster, yeah, matrix multiplication, these things. So you can just like make classical machine learning, take it one-to-one, but then instead of BLAS, you're calling QBLAS, and it's just like generically faster. Yeah. So this is like the generic side of it. But I mean, what I've been talking about today is the idea of a quantum learning model.
Yeah.
So can we have something which is genuinely quantum, but defined to classical data that kind of solves some kind of learning task? And for these kinds of models, I mean, we know that they are universal. Yeah. So if you make them large enough, they can express any function. Very nice. But I mean, are they particularly nice class of learning models? I don't know. Yeah. So this is like wide open. And I mean, now if you ask me, okay, for what kind of problem should I use this? I say no problem. Yeah, we don't know. Yeah, and especially if you want to have like an advantage in production, if today you want to deploy this model, then I mean, I say don't do it. Yeah, we pay a lot of money and get noise. Yeah, so it's just like really have to be mindful of what exactly we are doing, what we are saying we are doing, and what people want to do business with. Yeah, so also companies that do these quantum machine learning things, I think they do it more for this, like, okay, we want to understand what is the state of the art, and not in the sense of, okay, maybe it's also good advertising, but it's also it's not to say, okay, I can really route my, I don't know, airplanes better in this way. Yeah, because you can't.
Yeah, but in the terms, when you say that you classify, for example, in the paper, the symmetry groups, and you do it for different symmetry groups, and so this embedding, I mean, there is no relation with a physical system or a geometric or a manifold that can represent your data or whatever. So it's like totally theoretical at the moment.
Yeah, I mean, the thing is like, I mean, you can implement this. So, I mean, you can go to IBM, run these models on the quantum computer, so that you can do this. I mean, you can implement this runs, we can do small scale examples, all good. I mean, if I understand correctly, what you ask is like, okay, can I maybe find a physical system that has like already these kinds of symmetries inbuilt.
Yeah,
That's what you're asking?
Yeah.
Yeah, so yeah, I mean, we didn't look into it. It might be, I mean, some physical systems have like natural symmetries. I mean, usually you think about Hamiltonians. Hamiltonians have certain symmetries, which means the ground state also sometimes inherits these symmetries. And so people have been exploiting this for, I don't know, a gazillion years. Yeah. We also talk about that in the paper, so I also recommended to use it. But we didn't look into, might there be like an actual physical system that has a very amenable structure, for example? I mean, in the sense of like an analog quantum learning model. I mean, that could be an interesting direction to look into.
Yeah, because I mean, I saw in the paper that there is like appear somewhere the Z2 cross Z2 group or something. I think I have said. And for example, in string theory, the model I have studied is basically a geometry that is orbifolded, a manifold orbifolded by this group. So I mean, the symmetries appears all the time in the model. So yeah, I think it could be applied to some geometry. Or, I don't know, but
maybe yes.
I don't know.
Interesting. Well, that could be an interesting challenge, a research challenge for the community. To see if it looks any new direction or something. Yeah, take that into note. Let's go back to the chat. I think we are also running out of on the time. Is there anyone else? Final. I know I'm aware of Johannes' time.
Yeah, I mean it's okay. In classical tomorrow, there's George Sipperlin. He wrote something. Wait, I'll read it. Yeah, actually, George, can you elaborate a little bit more on this? Because I don't.
Okay, let me bring George. Let me bring George on stage. George is actually, let's see. Let's see, George. I think the stage is open, George. You can just join. I don't need to invite you. Yes, we can hear you, George. I think.
Okay, yeah, my computer is slow with the video, so I guess audio would be enough.
Yeah. No worries.
I guess my question would be if in the data world you do operations which aren't pure symmetries. So like a projection is not an invertible operation, but there still is some mathematical structure left. So I was wondering how that would map to the unitary representation.
So you want to say that you have your data on one hand side, you define some embedding, it's on the other side embedded, and you say, okay, for example, if I do a projection on the data side, how is the projection reflected on the other side?
Yeah.
Okay. Yeah, I don't know. We didn't look into this. It's a very, very unelaborate answer. Obviously, if you assume more structure, for example, if you say, okay, your data embedding is like this linear map into the Lie algebra, I mean, then it's mathematically more tractable, because then you just like you write down a matrix, you have a projector here, then you get, you can look what this does. But yeah, at the end of the day, yeah, I mean, I don't have insights into this. So let's say it like this.
Okay, yeah, thank you. It was just a thought.
Yeah. Well, it could be something to follow up with. You know, as you can see, and in emerging stuff, there are always like a question, because the field is so, I mean, the ideas are so new. You know, there are a lot of wriggle room for, you know, for like, you know, trying to, you know, exploit new questions, you know, questions that might open other new questions and so on. So, yeah.
Yeah, you would kind of lose the niceness of the of things commuting when you get to the representation side. But I'm wondering if there's anything that would still be left.
Yeah, I mean, I think this is like, I mean, it also depends on what you want to do with this knowledge at the end of the day, right? I mean, what the kind of task is that you want to solve, especially in the context of like a learning problem. where it's just like, okay, you're given some data, you want to classify it or something like this, right? And it's like the question, okay, when would these projections, for example, appear, and what's the operational meaning of it?
Yeah, I mean, it's like, say, in the context of your cute example, if your puppy is rotated in 3-dimensional space, as opposed to just the image being rotated, you will see a different view than you had.
Mm-hmm.
And it's maybe only if you rotate the puppy just a little in 3 dimensions, you can still see, oh, that's still the eyes and the nose and so forth. But at some point you lose that and you're seeing the back of its head or something.
Yeah, I think it's a very nice thought. I mean, I have really absolutely zero insight on this, but I imagine this is. I mean, people have probably thought about this, like in this, literature where they. I mean, it's also this pretty recent machine learning stuff where they try to extrapolate from an image to like a 3-dimensional object and these kinds of things.
But anyway, I didn't want to really sidetrack you too much. I really appreciated the talk, and it was a great overview. So thank you.
Thanks.
No, it was very, very interesting, and also a preview of, because after the course on Lie groups and representations, because a lot of the community members haven't taken a course of Lie groups yet, we will hopefully have Johannes to come in and do the mini school on geometric quantum machine learning. So hopefully by then, there will be some interesting development as well that could be mentioned on the side after the thing through in the context of the school as well. So yeah, so this is just a preview to see how group theory and representation theory topics that we will be covering in more depth in the context of Lie, have something very relevant in the thing, like state of the art emerging stuff, like the stuff that Johannes and his collaborators are working on. So yeah, so thank you so much for giving us these insights and the questions as well. Very interesting questions.
Thanks for the attention and for the opportunity.
Yeah. So this talk will be uploaded again on YouTube for everyone to rewatch. I saw something, a notification in the chat. What is this? Yeah. So, and I assume Johannes will be happy for some of you. If you want to follow up with some questions or something.
I mean, I think the easiest is just like shoot me an email. Otherwise, I mean, we can also arrange a short session depending on how much of an interest there is.
Yeah. So thank you so much, Johannes, for the interesting
my pleasure.
talk and instigating interesting questions as well. So I'll see you everyone in the next session.
Yeah, and Bambode, can we shortly meet in the green room?